This is lecture, yeah, lecture 24, part 2. And basically the idea is that we are going to continue to do some problems and today what we are going to do is we are going to talk about RC circuits, just as we talked about RL circuits. Remember, we are trying to get a response. In this case, we have introduced forcing functions into the picture now, and so we want the total response, and the total response, of course, is going to be both a natural response component and a forced response. Okay, so let's label this forced. Label this circuit. I'll label this lecture as forced RC circuits. And so let's do a problem. Here's an example. Here's a 10 ohm resistor in series with a 120 volt source. And then I have a switch. Let me call this A. And let me call this B. And this goes from A to B at T equals 0. And this is a single pole double throw switch, which we are now familiar with from a previous lecture. And then I have a 60 ohm resistor, a plus minus 50 volt source, and then this switch is connected to, no, let me finish this first. Here I have a (200 ohm resistor, and then the switch is connected to another resistor, uh, 50 ohms, and then there is this capacitor which is 0.05 farads. Okay, and that's my circuit. And what I want to do, and let me define this voltage here as Vc of t. All right, and what I want to determine in this circuit, so here's the problem. The problem states determine Vc of t, and in addition to Vc of t, I'm now going to ask also that we determine I through the 200 ohm resistor, okay, and I of t for all time. Okay? All right. So let me first address the voltage across the capacitor. Okay, so I'm going to determine the voltage across the capacitor first, and then I'm going to show you how to determine the current through the 2 ohm resistor. All right. So as I said, and this is the procedure is similar to our L circuits. And so in step 1 of the game, you look at the circuit. So let's look at the circuit for t equals 0 minus. All right? And by that I mean the switch is at A. Okay? The switch is at A, and it's been sitting there forever. That is, from minus infinity to t equals 0 minus, the switch is at A, and so the circuit, because now I'm focusing now on Vc of t, okay? So the circuit then becomes the following. A circuit becomes, here's my 120 volt source. This is my 120 volt source. There's my 10 ohm resistor. This is 10 ohms. There is this 50 ohm resistor. There is that 50 ohm resistor. And now I recognize the following, that with the switch at A, the circuit is a DC circuit. And if the circuit is a DC circuit, a capacitor is an open circuit to DC. So the capacitor is open circuit, and this voltage here is Vc at 0 minus. And now it becomes, it's trivial. One recognizes immediately that Vc at 0 minus is nothing else, by voltage division, if you like, by voltage division, Vc at 0 minus is nothing else but 50 over 50 plus 10 times 120. 50 plus 10 is 60. 60 goes into 120 twice. So this is equal to 100 volts. All right. So I have Vc at 0 minus, and I know one more thing, that the voltage across a capacitor cannot change instantly. Okay. And therefore, Vc at 0 minus must equal VC at 0 plus, okay? And so I know VC at 0 plus is equal to 100 volts, all right? And if you like, you can say over here, since the, since the capacitor voltage cannot change instantaneously. I think I can squeeze this in here. Oops. All right. So I've solved the problem at t equals 0 minus for VC at 0 minus. All right. Let's now start looking. I don't know where I should do this. Is it? All right. I'm going to now look at the circuit for t greater than or equal to 0, and maybe I'll do it on the next page. All right, and so let's go to the next page. So I'm now going to look at that circuit for t greater than or equal to 0. And the important point here now is that the switch is at B now, okay? So let me draw the circuit. Let me redraw the circuit for t greater than 0. All right. So here what I have is the following. I have this 60 ohm resistor. I have this plus minus 50 volt source. Then I have this 200 ohm resistor. Okay, and I have a 50 ohm resistor, and I have the 0.05. Let me put it over here, 0.05 farad capacitor, and this is the voltage VC of t that I wish to determine. So this is an RC circuit with a forcing function which comes on at t equals 0. The 50 volt source comes on at t equals 0. Remember, the circuit is sitting somewhere up to t equals 0 minus, and then at t equals 0 plus, at t equals 0, we've switched on this different source, this 50 volt source, into the circuit, and I know immediately that I can write down this. Oops, what happened here? Oh, I can immediately write down that the solution Vc of t is some Vc natural of t plus Vc forced of t, and this I know has to be of the form a e to the power of minus t over tau plus Vc at infinity. Okay, so what we have to determine now in the circuit is the constant A, the time constant tau, and the value of the constant we see at infinity. All right, so first let's determine tau. All right, so in order to determine tau, I kill the circuit. All right, I kill. So let's draw the killed circuit. All right, let's draw the killed circuit. Killed circuit means short circuit all voltage sources. Okay, so I'll put down here short circuit voltage source. All right, and so if I short circuit the voltage source, I get the following circuit. This is 60 ohms. This is 200 ohms. This is 50 ohms. This is my capacitor. Okay, this is my capacitor, and this is 0.05 farads. And what I want to do is I want to look across these two terminals in here and determine R equivalent. All right, and this is rather simple because I mean you can do it any way you want, but you can first say these two are in parallel, and then the combination of those two in parallel is in parallel with the 50 ohm resistance. And I won't belabor the point. I'll simply write down R equivalent equals 24 ohms. All right, and therefore tau equals R equivalent C, right? I mean, the circuit has now become an RC circuit. R equivalent and a C equivalent. In this case, C is 0.05 farads. And so this becomes equal to 24 times C is 0.05, and this becomes 1.2 seconds. And therefore I can immediately say, therefore Vc natural of t is equal to A e to the power of minus t over 1.2. All right? Okay. So I've now got tau. The next thing I want to do, and I'll do it over here. All right. So we go from here, to here. And next thing I want to do is determine Vc at infinity. That is, I want to look at this circuit for t tending towards infinity. Okay, this will give me, this is for my forced response, right? This is for my forced response. All right. So what does my circuit look like for t tending towards infinity? Well, my circuit for t tending towards infinity looks as follows. It looks like it's got this 50-volt source. It's got my 60 ohm resistor. There's my 200 ohm resistor. There is my 50 ohm resistor. Okay. And then remember, for large T, the transient response is dead. Okay, the transient response is long gone. Transient responses die down within 4 to 5 tau, right? As we've learned in the past. And consequently, for t tending towards infinity, this is a DC circuit. But if you have a DC voltage source, then the capacitor is an open circuit. So then this becomes plus minus Vc at infinity. But this is trivial because now you see that these two are in parallel. And what does that give you? This is 200 times 50 over 200 plus 50. That's 250. 50 goes into 255 times. 5 goes into 24 times. So this circuit then becomes equivalent to 50 volts, 60 ohms, and as I just said, 40 ohms, and this is plus minus Vc at infinity. And again, by voltage division, it becomes evident that Vc at infinity is 40 over 40 plus 60 times 50. 40 plus 60 is 100. 50 goes into 100 twice. 2 goes into 40 20 times. So Vc of infinity is 20 volts. Okay? So now I've got Vc of infinity, I've got tau. The only thing remaining is to determine the constant A. All right? Well, at this stage of the game, let's do the following. At this stage of the game, what do I know? At this stage of the game, I know that Vc of t is equal to A e to the power of minus t over 1.2 plus Vc at infinity, which is 20. Now, the only thing remaining is the determination of the constant A. And so if I want to determine the constant A, I can determine it by the condition of the fact that I know on the previous page, Vc at 0 equals 100. We know that from the previous page. And so at 0, the right-hand side of the above equation becomes A plus 20 and therefore A equals 80. All right? And so I can write down my total solution for t greater than 0 to be Vc of t equals AT e to the power of minus t over 1.2 plus VC at infinity, which happens to be 20. And so this is my solution for t greater than or equal to 0. All right. So let me plot this function for you. Let me now plot the entire VC of t for all t. All right. So let's go on to the next page. And so I'm going to plot VC of t. This is t. This is VC of t in volts. This is seconds, of course. Now, where was the circuit for t less than 0? It was sitting at 100. So it's sitting at 100. Okay. Where is the circuit being pushed to? That is, what is the source, that voltage source, that 50 volt source forcing the circuit to go towards? That's VC at infinity, and we know what that is. That's 20 volts from the previous page. So it's heading towards 20 volts. And how is it heading towards 20 volts? Well, it's heading towards 20 volts exponentially. So, so the response is like this. That's what the voltage, that's at 100, okay, because it's a continuous function. So that's my voltage, all right, for all time. And you can see that the natural response is a transition from the initial to the final values with a time constant of 1.2 seconds. All right? Okay. Now let's go on with the problem and determine I of t for all time. All right. So maybe what I'll do is, yeah. Okay. So let's do it over here. Let's next determine I of t. This current was through that 200 ohm resistor, all right, on the first page, for all t. So again, back we go. First we look at the circuit at t equals 0 minus, and at t equals 0 minus, don't forget the switch is at A, okay, and so the circuit with regard to the current I is simply the following. It's simply the 60 ohm resistor, the 50 volt source, and the 200 ohm resistor, and this current here is I at 0 minus. And therefore, I at 0 minus equals, the voltage is 50, the resistance is 60 plus 200, and this turns out to be 0.192 amps. All right, so I now know I at 0 minus. Now, let's look at the circuit for t greater than, let's look at the circuit for t greater than or equal to 0. All right. And I know a lot of things already about the circuit. All right. Number one, I know tau. Tau known, because the response of the circuit, any other response of the circuit, must also be of the form AE to the power of minus t over tau plus a forced response. Okay, so let me write that down. For t greater than 0, I of t equals some constant a e to the power of minus t over 1.2, remember that was our tau, plus I at infinity, right? The forced current at infinity. So let me go on here now. Let me go on here now and look at the circuit for t tending towards infinity. I've already done this. All right, I've already done this, but what I want is in that circuit, I want I of infinity. So let me redraw the circuit. Let me redraw the circuit, which I had on the previous page, and that circuit was the following. That circuit was 50 volts. This was 60 ohms. This was 200 ohms. And this current here is I at infinity. But then if you look back, you'll see there was another 50 ohm resistor here, right? And of course, since this is a DC circuit, the capacitor is an open circuit, and this was VC at infinity. And if you recall, we already determined VC of infinity, right? VC of infinity was 20 volts. And so we know this was equal to 20 volts. Well, if I know VC of the voltage across the 200 ohm resistor, I immediately know, therefore, I of infinity is VC of infinity over 200, which is 20 over 200, and this is equal to 0.1 amps. Okay? So now the situation is the following. Now the situation is that I know that I of t, this is all under the heading of t greater than or equal to 0. I of t is the natural solution, a e to the power of minus t over 1.2 plus I of infinity, which is 0.1. All right? And all that remains is to determine the constant A. Well, in this case, this is a current through a resistor. So the current through a resistor, we know, can change instantaneously. All right? And therefore, knowing the current at 0 minus is of no help to me. I actually have to determine the current through the 200 ohm resistor at 0 plus. All right? So let me now draw the circuit at t equals 0 plus. Okay? So here's the circuit at t equals 0 plus. At t equals 0 plus, I have my 60 ohm resistor. I have my 50 volt source. There is this 200 ohm resistor. This current here is I at 0 plus. Then there is the 50 ohm resistor. And then there is the capacitor. But I know the value of the voltage across the capacitor at 0 plus. Because I know VC at 0 minus, I know VC at 0 plus. So at t equals 0 plus, I can replace the capacitor with a voltage source VC at 0 plus equals 100 volts. So once I know that, the problem is over. Therefore, I at 0 plus is simply equal to 100 volts over 200 ohms, and this gives me 0.5 amps. So now I know I at 0 plus, and therefore I can determine the constant A in that equation above. And let's do that. So I at 0 plus, which is equal to 0.5, is equal to A plus 0.1, and this gives me that A equals 0.4. So let me now write all of this down on the next page. Remember that for t less than 0, the current I is at 0.192, and it's heading towards I of infinity, which is 0.1. And at 0, there's a jump. Okay, so let me rewrite this. Let me rewrite this equation for you. So I of t is equal to 0.192 for t less than 0 is 0.1 plus 0.4 e to the power of minus t over 1.2 for t greater than 0. Okay? Before I write it so that it's valid for all time, let me plot the function for you. Okay, let's plot this function, and then we'll rewrite this in a more fanciful way. All right, so here goes. Let me draw the circuit for you. Not the circuit, the response. This is t in seconds. This is I of t in amps. So, where is the circuit for t less than 0? It's sitting at, let me do it here. It's sitting at 0.192. Now the switch is switched from A to B, and the current through the resistor then jumps to 0.5. Okay. And then there's this natural transient response going all the way to the forced response. What is the forced response? The forced response, if you recall, is 0.1. So here, oops, no. This is 0.1. This is 0.1. And it decays to this, the response decays to this value exponentially. All right. Let's do this carefully. Yeah. Okay. So that's what the response looks like. Okay, that's the current response. Remember, in this case, the current can change instantaneously. But in order to determine the value of the current at 0 plus, what did I do? I used the fact that I knew the voltage across the capacitor at 0 plus. So if I put in that value, again, I'm solving a DC circuit problem. Okay, so I'm always solving a DC circuit problem. That's why we spend so much time in the first third of the course on DC circuits. All right, now, as promised, let me write this so that the expression is valid for all time. And I'll show you two ways of doing this. I can write that above expression as follows. I can write it as I of t is equal to 0.192 plus minus 0.092 plus 0.4 e to the power of minus t over 1.2 multiplied by the unit step function u of t in amps. Remember, u of t is 0 for t less than 0 and is 1 for t greater than 0. So you can see that this expression is correct, of course, for all time, is exactly the same as the expression above the figure. I can also write this expression in another way. And that's the following. By using a slightly different, well, again, I'm using a step function, unit step function, okay? So I can say, or I'll write this as I of t equals 0.192 u of minus t, okay, plus 0.1 plus 0.4 e to the power of minus t over 1.2 close paren u of t amps. What is u of minus t? Well, u of minus t is unity for positive argument. So it's unity for t less than 0, and it's 0 for negative argument, which means it's 0 for t greater than 0. So let's draw that picture. Oops. What is u of minus t? U of minus t is 1 for t less than 0. This is 1, and 0 for t greater than 0. Okay? All right. So let me summarize all this. Okay? Let me summarize all this for you, as I did for the previous case. Let me open this. Hold on. All right. So here is the summary. Which I believe proves useful. So step 1, draw circuit at t equals 0 minus. Okay, this is a DC circuit. Okay, with capacitors open circuited. And then you determine voltage across capacitor VC at 0 minus. Okay. Recall that VC at 0 minus is equal to VC at 0 plus, as the voltage across the capacitor cannot change instantaneously. ESLY. Okay. All right. 2, consider the circuit for t greater than or equal to 0. All right? The solution is of the form Vc of t equals a e to the power of minus t over tau plus Vc at infinity. Okay? So now you start determining the various constants, a, tau, and Vc of infinity. To determine tau, you kill circuit. Kill circuit. Kill circuit. This means, in general, open circuit all independent current sources, short circuit all independent voltage sources. Okay? Determine R equivalent, okay, and then tau equals R equivalent C, in general C equivalent. Okay. For consider circuit for t tending towards infinity. This is a DC circuit with capacitor open circuited. Solve for Vc of infinity. Remember, this is a constant. All right? And then we have 5. So we've determined tau, we've determined Vc of infinity. All we now need to do is determine A. Since Vc at 0 minus equals Vc at 0 plus, determine A by applying this initial condition. Okay, that is Vc at 0 equals A plus Vc at infinity, and this will give you that A equals Vc at 0 minus Vc at infinity. All right, and last but not least, the solution for t greater than or equal to 0 is then Vc of t equals the constant a, which is Vc at 0 minus Vc at infinity e to the power of minus t over tau plus Vc at infinity. And that's it. Okay? So, for circuits which can be reduced to an R equivalent and a C equivalent, this is the process that one must follow. It's very straightforward. Recall that at each point in the game, you are essentially solving a DC circuit problem. And that we know how to do. All right? So with that, let me end lecture 24, part 2. All right. Take care. Bye-bye.